So today we're going to revisit the idea of talking about constant rates. So we have been talking about, or we have talked about constant rates, but it was at the very beginning of the year if we talked about it at all in 8th grade. We definitely talked about constant rates in 7th grade, but you might not remember them as well as you might think. So today we're going to revisit this idea of constant rates, but still look at constant rates in terms of linear equations. So we're going to get information from story problems. We're going to write a linear equation from those story problems. And then we're going to graph the linear equation and solve for anything that they're asking us to solve for. So that's what we're going to be doing today. But I just want to do a really quick review of what a constant rate is, just in case you've forgotten. So you can see my screen here. And I'm going to write some stuff at the very top of my screen before we actually look at this exercise. So remember that when we're discussing constant rates, we're discussing a ratio. And remember, we can write a ratio in two different ways. We can write it as x or y to x, or we can write it as a fraction, y over x. They mean the same thing. So we're comparing two numbers in some way. So today, as we're looking at these story problems and we are revisiting this idea of constant rates, we're going to use this form right here of y over x to represent so for the first exercise, we would be representing square feet per minute. So y would be your square feet and the minutes would be your x value. So I'm going to take you through these problems, so I don't want you to get confused yet. But we're going to revisit this idea of constant rate in terms of linear equations. So I have just a really quick example for you guys before we even get started with our exercise. So I'm just going to write EX up here. And my example is that Erica is working at a constant speed of 3 miles per hour. So she's working at 3 miles per hour. And remember that when we're looking at constant rates, what we're looking for is something per hour, so miles per hour, or let's see, square feet per minute. So we're looking at something compared to 1. So if we're looking at miles, we want to know how far they're going in just 1 hour. If we're looking at minutes, or square feet, we want to know how far they're going in just 1 minute. So we're always looking at comparing it to just 1. So in my example here, Erica is walking at a constant speed of 3 miles per hour. So we can express her motion as y over x equals 3 over 1, because that y value is representing your miles and the x value is representing the number of hours. So we're saying in 1 hour, she is traveling 3 miles. So we're looking at this idea of what's happening in 1 minute, what's happening in 1 hour, what's happening in 1 second, and so on. So we're going to represent it as this equation of y over x equals the number of miles or the number of feet or whatever per the number of hours or minutes or seconds or whatever. So as we represent this equation, y over x equals 3 over 1, we know that 3 over 1, we don't need to represent it as 3 over 1. We can just say it's just 3. So this equals 3. Now, we have this idea, we've been looking at this way of writing equations as the slope-intercept form. And the slope-intercept form is, remember, y equals mx plus b, where m is our slope and b is our y-intercept. So we still want to represent these equations as y equals mx plus b. So even though I've written this as y over x equals 3 over 1, which is technically y over x equals 3, we can still represent these equations as linear equations in the form y equals mx plus b, because if I multiply both sides of my equation by x, it gets rid of that x in the bottom of my fraction, and I'm left with y equals 3x, which is that slope-intercept form. In this case, our y-intercept would be 0, so we could just say plus 0, but we're not going to worry about that for this lesson. So I want to take a look at some exercises because I don't want that to have confused you guys. So let's look at our first exercise here. It says Peter paints a wall at a constant rate of 2 square feet per minute. Now, we did look at constant rates a little bit in at the beginning of this year. And remember, we said it was really important that they told us that it was a constant rate. If they didn't tell us it was a constant rate, we couldn't do the problem in the same way. So they told us that it's a constant rate, which is really great. And they told us that he's painting this wall at 2 square feet. So I'm going to put 2 square feet per 1 minute. Now, you don't have to include your units because they've already given us the units, but I'm just explaining this to you guys. So we have 2 square feet per minute. And remember, we represent that as y over x. And they tell us, assume he paints an area y, so we put our y in the correct spot, in square feet after x minutes. So we put our minutes at the bottom of our equation. So it says to express this situation as a linear equation in 2 variables. So remember, I already told you that even though this is the way that we would write our equation, we can really represent it as y equals 2x because we're able to multiply that x by both sides of the equation to make this equation into a slope-intercept form. So we're expressing this situation as a linear equation in 2 variables by saying y equals 2x. So we just took that information and put it into an equation very simply. So in our next problem, they're going to ask us to sketch the graph of this equation. So I'm going to flip to my next slide, and here's our graph, and they want us to sketch the graph of that linear equation. So remember, my linear equation is y equals 2x. And remember, when I'm sketching a linear equation, I need to know what my y-intercept is. So remember, if we don't see a y-intercept in our equation, it is 0. So this is actually y equals 2x plus 0. So that lets me know that my graph is going to start at 0, 0 because my y-intercept is 0. So I'm going to plot a point right here at 0, 0 on my graph because that's where my line is going to start. Now, remember that this is your y-intercept, so that tells you where your graph is starting along the y-axis. And then our equation also tells us the slope. And remember, the slope tells us how far up and over we need to move from each point on our graph. So our slope right here is 2 over 1. Don't forget that we're always looking for that number on the bottom of our fraction as well. And if we have a number that's represented as just 2, we know that that number is actually over 1. So our fraction is 2 over 1. And so that means from this 0, 0 point on my graph, I need to move up 2 units and over to the right 1 unit. But remember, I always told you guys that you have to pay attention to the units. Because if you look along the y-axis here, we're going up by units of 2. So each unit or each square on this graph is 2 units. So I'm not actually going to go up 2 units. I'm just going to go to this 2, and then I'm going to move over 1 unit because I've just gone up 2 units technically. There's technically a 1 right there. So from this point here, I'm going to go up to 4 because from 2 to 4 is 2 units. So here's I went up 2 units, and I'm going to go over 1 unit. And I have another point on my graph right there. Up 2 units, over 1 unit, there's another point on my graph. So I could keep going like this and create this really nice straight line where I can connect all of these points. And this is representing the graph of my linear equation. So here is the graph of my linear equation right there. I used the slope and my y-intercept in order to create this graph. So in our next problem, they're going to give us, or in the next part of this problem, they're going to give us some information, and they're going to ask us to determine the total area that he's painting after a certain amount of minutes. So I'm going to flip to the next slide, but I'm going to keep in mind that my equation is y equals 2x, okay? Where that y value is representing the area that he's painting, which is square feet, and that x value is representing the number of minutes. So I'm going to write that out here for us. I'm going to write y equals area and x equals minutes, okay? So we're going to take a look at, and this is just information that they told us in that very first problem. So let's take a look at this question. It says, using the graph or the equation, Determine the total area he paints after 8 minutes, 1.5 hours, and 2 hours. Note that the units are in minutes and hours. So the reason that they told us to note that the units are in minutes and hours is because in our equation uses minutes. So that means that we have to convert these hours to minutes in order for them to be plugged into our equation. So 8 minutes is easy. We can just plug 8 minutes into our equation and solve for y to determine the area that he's painting after 8 minutes. So y equals 2 times 8, because remember that 8 is an x value. So we're plugging 8 into our equation. And so that means that y equals 2 times 8 is 16. So y equals 16, meaning that he's painting an area of 16 square feet after 8 minutes. Okay, remember our units are square feet. Now, let's look at after 1.5 hours. So firstly, we need to convert those 1.5 hours into minutes. So as I'm thinking about this, so I've got 1.5 hours, and I know that in an hour, there are 60 minutes. Okay, so, sorry, there's something on my screen. I've got, that backfired on me real quick. I've got I'm going to multiply that by 1 minute. And no, I'm sorry, I did this incorrectly. So I'm going to say 1 hour on the bottom, multiplied by 60 minutes. So I want to divide this. Hold on, guys. I'm going to do this in a different way because this is confusing me for some reason. Okay. So I know that in 1 hour, there are 60 minutes. So I've got 60 minutes here. And I've also got half of an hour. And in half of an hour, I know that half of an hour is 30 minutes. Okay. So I'm going to add those up. So I've got 90 minutes in an hour and a half. Okay. So now I can plug those 90 minutes into my equation. So y equals 2 times 90. And when I multiply 2 times 90, I get y equals 180. Remember, our units are square feet. So that means that in 1.5 hours, he can paint 180 square feet. Okay? Now, let's do 2 hours. And I'm sorry, I have to continue it over here. So here's our 2 hours. Remember that an hour is 60 minutes, so 1 hour is 60 minutes. So if we're doing 2 hours, we're going to multiply that by 2. So we get 120 minutes in 2 hours. So I'm going to use my equation y equals 2 times 120 minutes, because I had to convert that to minutes because that's what my equation was requiring of me. And when I multiply 2 by 120, I get y equals 240 square feet. Meaning in 120 minutes or 2 hours, he's going to paint 240 square feet. So we're using the information that they're giving us, firstly, to determine an equation from our constant rate. Remember, when we're talking about in slope-intercept form, our constant rate is represented as our slope. So this would also be constant rate. So I'm going to write that on here as well. Constant rate, okay, is represented as our slope. So that's why we can represent these situations as linear equations in two variables with that constant rate as our slope, because the constant rate is represented as the slope. So that's why I was able to sketch the graph of my linear equation so easily, because I knew that my y-intercept was 0, but also that my slope was 2. So I was able to go up 2 units and to the right or left 1 unit, and in this case to the right 1 unit because it's positive. And then in this situation, they gave me some information and I was able to plug it into my equation because I knew that y was area and x was minutes. So I was able to convert from hours to minutes and then plug those minutes into my equation. So we're going to take a look at a couple of more examples that look a lot like this one, but are a little bit different. So they're asking us just a little bit different things. So I'm going to move on to my next question. And number 2 says, the figure below represents Nathan's constant rate of walking. Part A says Nicole just finished a 5-mile walkathon. So remember, miles are our Y value, so this equals Y. And it took her 1.4 hours, and hours are our X value, so this equals X, okay? All right, so assume she walks at a constant rate. So they're telling us she walks at a constant rate. Let Y represent the distance Nicole walks in X hours. Describe Nicole's walking at a constant rate as a linear equation in 2 variables. So this is where things get just a little bit different. So we're still using that form Y equals mx plus b, where our constant rate is our slope. But in this case, they told us she's walking at a constant rate, but they didn't give us that constant rate. They told us that she's walking 5 miles in 1.4 hours. Well, she walking 5 miles in 1.4 hours is not my constant rate. My constant rate would be me knowing how many miles she's walking in just 1 hour. So I need to do some division so that I know how far she's actually walking in just 1 hour. So I'm going to do this in actually 2 ways, and it doesn't matter to me which way you choose to do it. So I would be happy if you simply wrote your equation as y equals 5 over 1.4x, keeping in mind that that is not her constant rate. Her constant rate would be you dividing 5 by 1.4, and then you would know that she's walking 3.57 miles in 1 hour. So that would be her constant rate, and you need that information as you are comparing 2 constant rates. So I want you to keep that in mind. So you could do that in one of 2 ways. You could also represent this as y equals 3.57 X, because she's walking 3.57 miles in just 1 hour. So that would be 3.57 over 1, okay? So I'm fine with either way that you write this. Now, before we move on to part B, where they ask us to compare these 2 constant rates of walking to see who's faster, we need to figure out Nathan's constant rate of walking. So we're going to do that from this graph right here. And we're going to pay very close attention to the scale, because notice along the y-axis, our scale goes up by 2 units each time. So let's look at, we're going to use, remember we're trying to find the slope. So we're going to figure out what the slope is from each of these points. So we're going to start at 0, 0. And we need to figure out how many units up and to the right do we need to move to get to this next point right here, which is 4, 1. So if I'm paying attention to my scale, I need to go up 2 units to get to 2 and 2 more units to get to 4. So I'm going up 4 units, so y equals 4, and I'm going to the right 1 unit. So that means my scale is 4 over 1x. So I would represent this equation as y equals 4x. That is the equation for this line. So Nathan's constant rate of walking is 4 miles per hour. So he is walking 4 miles, I'm going to write this out, 4 miles in 1 hour, okay? Whereas Nicole is walking 3.57 miles in 1 hour. So when I flip to the next slide, they're going to ask us to compare, or they ask us who walks at a greater speed, and explain. So as we're looking at this, we're comparing the slopes, okay? We're comparing slopes, and slopes tell us rates of change. So comparing slopes, and what we're going to understand is that whoever has the larger slope is walking at a greater speed. So we're going to look at this, and we know that 4 miles in 1 hour is faster than 3.57 miles in 1 hour. So Nathan walks at a greater speed than Nicole does. So Nathan walks at a greater speed because he has a larger slope. Because I'm going to say his rate of change is larger. And so I'm going to represent this as an inequality. So Nathan walked at 4 miles per hour, whereas Nicole walked at 3.57 miles per hour. So what I'm saying here is 4 is greater than 3.57. And because 4 is greater than 3.57, Nathan is walking at a greater speed than Nicole is. His slope is larger than Nicole's, or his rate of change is larger than Nicole's. He is covering a larger distance in 1 hour than Nicole is. So that is what they're asking us to do in each of these exercises. They're asking us to compare rates of change or slopes to determine who is doing something faster. So I'm going to move on to the next question now. And it says, Susan can type 4 pages of text in 10 minutes. So remember that minutes are, or time is always going to be our x value. So x equals time. And whether we have miles or square feet or pages of text per minute, that's always going to be our y value. So y is pages of text. Now remember, constant rate is something that is per one, in this case, minute. So we want to know how many pages she can type in just 1 minute. So we're going to write our linear equation as y equals 4 over 10 x. And that's perfectly acceptable for writing the linear equation to represent this situation. But keep in mind, you need to divide 4 by 10 in order to figure out her actual constant rate. How many pages is she actually typing in 1 minute? So we can actually just simplify this fraction, and that's okay too. So y equals 2/5 x, meaning in 5 minutes, she's typing 2 pages. So we're going to actually go ahead and divide 2 by 5. So we get y equals 0.4x, meaning that she's not even typing a full page in 1 minute. She's typing 2/5 of a page in 1 minute. So what we're saying here is that she can't type a full page in 1 minute, but we can represent our linear equation for this situation in any of these 3 ways. Any of those 3 ways would be perfectly acceptable, as long as you keep in mind that the only way that is telling you the actual constant rate is this way right here, saying she's typing 0.4 tenths of a page in just 1 minute. Okay, so please keep that in mind. All right, so let's look at part B. It says the table of values below represents the number of pages that Anne can type, Y, in a few selected X minutes. Assume she's also typing at a constant rate. So she can type 2 pages in 3 minutes. So we would represent our linear equation as y equals 2/3 x. But remember, we're interested in how many pages she's typing in just 1 minute. So that means that we would actually have to go through and divide 2 by 3, and we would determine that y equals 0. We'll round up 67x. So she's typing 2/3 of a page in 1 minute, whereas Susan is typing 2/5 of a page in 1 minute. And because 2/3 is larger than 2/5, we can confidently say that Anne is typing faster than Susan is because she has a higher constant rate. So we're going to say Anne types faster than Susan because Anne's constant rate is larger, meaning she is able to type more in just 1 minute. So I'm going to represent this situation, or who's typing faster, as 2/3 is greater than 2/5. And that's just telling me that Anne's constant rate is 2/3. She's typing 2/3 of a page in 1 minute, whereas Susan is typing 2/5 of a page in 1 minute, or 0.4 of a page. So not an entire page yet, okay? So that is what we're saying in terms of determining who is typing faster. So I have just one more example for you guys before I set you free, or if you have any questions for me. So let's move on to that next question before my recording cuts off. So it says Phil can build 3 birdhouses in 5 days. Assuming he builds birdhouses at a constant rate, write the linear equation that represents the situation. Okay, so remember, y is the number of birdhouses that he's building, and days is his time. So he is building y equals 3 over 5x. That's how we're going to represent this situation. In order to determine how many birdhouses he's actually building in just one day, we would need to divide 3 by 5. So we could represent this as y equals 0.6x. And that means he's not even able to build 1 birdhouse in one day, which makes complete sense if he's building 3 birdhouses in 5 days. So he's only building 0.6, he's only building 6/10 of a birdhouse in one day. So we're keeping that in mind as we look at Carl's constant rate of building the same kind of birdhouse for part B. So the figure represents Carl's constant rate of building the same kind of birdhouses. And then they're going to ask us who is building birdhouses faster. So we need to look at this graph of Carl's constant rate of building the same type of birdhouses and create a linear equation for this information. So these units are going up by 1, so we're good there. So we want to know how far up and to the right we need to move to get to this next point from 0, 0 to 4, 3. So we need to move up 1, 2, 3 units. And we need to move to the right 1, 2, 3, 4 units. So this is his linear equation to represent the number of birdhouses that he's building at a constant rate. So if we were to divide 3 by 4, y equals 0.75x, meaning he's building 3/4 of a birdhouse in just one day. So not quite, larger than Phil is building. So he's building more of a birdhouse in one day than Phil is building. So they're asking us who is building birdhouses faster, and we can say that Carl is building birdhouses faster than Phil is because Carl has a larger constant rate. Carl has a larger constant rate. And we're going to represent that as, we're going to say 3/4 is larger than 3/5. So we know that Carl is building birdhouses faster than Phil is. So that is all I have for you guys as far as our lesson for today. I actually think it would be really awesome if we could also go through the science lesson. So we might do that as well. So I'm going to